Hello students, today we'll be dealing with a very interesting topic that's called buoyancy. We'll see how the buoyancy originates and how does it manifest in the flotation of the objects, the movements of ships that we see on the in the oceans. So let's start the topic. Let's move to the new topic, buoyancy and Archimedes principle. What exactly is buoyancy? Buoyancy is the net force of the fluid on the cylinder or any object that is kept within a fluid. It is simply the net force that is exerted by the fluid on the object that is kept. Here it is, the cylinder. Now, where from this net force comes in? Now, as we know that the pressure increases with depth. The pressure what will be present at this depth, suppose this is H, and the lower portion of this cylinder, suppose this is H dash. Now the pressure at H will be smaller than the pressure at H dash because the pressure increases with depth. So that means the pressure at this point is higher than the pressure at this point. Now if they both have the same cross section area, the force that will be acting at this point, F down, it will be smaller than F up, that is acting at the bottom, because the pressure here is greater, which implies that the force also is greater at this point. Since the force at this point is greater than the force here, there is an upward force that is acting. Here we have considered this of equal cross sectional area and we get this. That means the upward force that acts on a body that is immersed in a liquid, partly or wholly, there is a pressure from the bottom that is greater than the pressure from the top. That's why there is an upward pressure. Now, the pressure in the liquid that exerts the net force upward on the cylinder. Now this net force, if we find out the magnitude of this will be the force that is acting in the upward direction, that is at the bottom face, minus the force that is acting on the top face, that is the force that is acting in the downward direction. Now this net force is called the buoyant force. This net force is called the buoyant force. Now it should be very clear at this point of time that this buoyant force is not a special property of fluid. It's not that just that there is a fluid that there is a buoyancy force. It is the Newton's law that is giving you the buoyancy force. It's simply the unbalanced forces that are giving you the buoyancy force. Buoyancy force is just a fancy name for that unbalanced force. It's not a special property of fluid. And as we know, fluid means both the liquids and gases. So buoyancy is simply an unbalanced force occurring because of the pressure differences at different depths, and it is simply coming from the Newton's law. It's not a special force. Now when an object or a portion of an object is immersed in a fluid, it displaces the fluid. Now we know that if we will submerge any block, any body within a fluid, what it will do is that it will displace the fluid, and its volume will be equal to whatever the volume is submerged, because it's a solid and we are putting it inside, so it will displace the volume. Now the displaced fluid's volume, the fluid that has been displaced, its volume, it equals the volume of the portion of the object that is immersed in the fluid. So the portion, the part of the object that has been immersed in it will be equal to the volume of the liquid displaced. And here from there comes in the Archimedes principle. What it states is that the fluid exerts an upward buoyant force Fb, and we have seen how it comes in the picture. It is because of the pressure difference and because of the Newton's law. So this upward buoyant force on an object that is immersed in or floating on the liquid. Floating means something is partly immersed. Now the magnitude of the buoyant force equals the weight of the fluid displaced by the object. Archimedes principle, it states that the magnitude, we have seen what direction the buoyant force acts. Now what is the magnitude of this force? The magnitude is equal to, it is the weight of the fluid displaced. You have to consider the weight of the fluid that has been displaced. It's not the weight of the block, it's the weight of the fluid that has been displaced by the object. Now suppose the fluid has density rho f. Now we are assuming that suppose the fluid, let's consider this, it is filled with a liquid, it has a density rho f, density of the fluid, and the object displaces a volume Bf of the fluid. Now suppose I put an object like this, here I am showing it partly submerged, it displaces a volume. Now the volume displaced is this volume of the block that you see, this volume will exactly be equal to the volume of the fluid displaced, and we assume that this volume is Vf. Now the Archimedes principle in the equation form is, this is what the Archimedes principle states, we have seen here is that the buoyant force that will be acting, which is Fb, is the weight of fluid displaced. Now the volume of the fluid displaced is Vm, the density of the fluid displaced is this. So this is the mass of fluid displaced. Now if we have the mass of the fluid displaced, its weight will be mass of the fluid displaced into g. This weight is the buoyant force. And this gives you this when you put the value of the mass of the fluid. Now let's see what happens in the case of a floating object. Now here, as given in the picture, an object of density rho naught, it has been given density rho naught and volume V naught, its volume is V naught, is floating on a fluid of density rho f. This is of density rho f. Now the submerged volume of the object, say it is given here, as you can see from the picture also, this portion is submerged. Now this volume will exactly be equal to the volume of the fluid displaced, because this is a portion that has gone into the liquid. Now this floating object, the buoyant force that is experienced by this floating object is this from the Archimedes principle, as we have seen in the last slide. Density of the fluid into volume of the fluid into g. Now this is what? Density of the fluid into volume of the fluid. This must be equal to the weight of the body acting downward, because it is floating. Now if anything is floating, what it means? It means that the body is in static equilibrium. That means the net forces that are acting on this body are zero. The forces that are acting upward, we know the only force that is acting here is the buoyant force, because this is a resultant of all the forces. So all the pressure forces, all those forces that comes to your mind, they are giving you the buoyant forces. So they are all added up here. This is the buoyant force, and then you have the weight mg. Here m is the mass of this whole body, because the weight that will be experienced is the total mass. So this is mass into g, this is the buoyant force Fb. Now we know that the buoyant force is given by this, density of the fluid into the volume of fluid into g. Here Vf is the volume of fluid displaced. Now this should be equal to the mass of this into g, if it has to float. If it has to float, this must be the condition. Now the mass of this block can be written in terms of its density into volume. So the volume V naught is the total volume of this fluid. So we write it, rho naught is its density, V naught is the total volume. So this one is the total mass. This is the mass of the whole block. So m into g is its weight is equal to the buoyant force, which is given by this formula. Now the volume of the displaced fluid. Now as we can see that since this is floating, from this very equation you can get it from here, that if you cancel out, you have rho f into Vf is equal to rho naught into V naught. That gives you the volume of the fluid displaced is rho naught by rho f into V naught. Now rho naught by rho f is the density of the fluid, this is this, and rho naught is the density of the block. Now Vf, we know that the volume of the fluid displaced is less than V naught. For this, rho naught has to be less than rho f. That means its density has to be less than this for it to float within the liquid. So the density of this rho naught must be less than this, because volume of the fluid displaced cannot be greater than V naught, because the maximum volume that this object will be able to displace will be equal to its own volume, that's V naught. So it will be equal to V naught only when this is equal. Otherwise, this will always be less. So if this is less, that means rho naught has to be less than rho f. So that gives you this condition. So for the floating to happen, its density must be less than the density of the fluid. Let's see a question based on this. A cubical block of wood 10 cm on a side. So we have a cubical block of wood. It is 10 cm on the side. It floats at the interface between oil and water. So let's take that this is the interface. These are the two layers. Now let us see which layer is oil and which is water. We'll have to deduce it from here. It's not given here in the question. The wood is of 10 cm. Okay, it's given that you have a block its sides are 10 centimeters. Floats at the interface between oil and water with its lower surface horizontal. It's given that the lower surface of this cube is horizontal and 4 centimeter below the interface. So it's like this. If you see from the front, it is like this. This is 4. Now it's given that this is 10 centimeter inside, so that means this one is 6 centimeter. Okay. So now let's see what are the things that are given. The density of the oil is given as 0.6 gram per centimeter. Now we know that the density of water is 1 gram per centimeter. Okay, per centimeter cube. So this is also cube. This is gram per centimeter cube. Now the question being asked is what is the mass of the block? It's floating like this. Now the first question that comes in mind, whether oil is above or the water is above. Now as we have seen in the last slide that the lower density thing remains at the top. It floats. Whatever has the lower density is the one that floats. Now since the density of oil is smaller than this, so this one is oil. This one is water. Because it has to flow, it will be above. It has the density that is lesser. So now we have been asked what is the mass. Now it's given that it's floating. That means the net force is 0. Net forces are 0. Now what are the forces acting? One is a buoyant force that we have seen acting in the upward direction. Another is weight mg that is acting in the downward direction. Now this mass m we have to find out. So what we will do, we will try to find out the buoyant force. What is the buoyant force that is acting? Now the buoyant force acting due to the portion submerged in oil, we will first find out this. Buoyant force due to this portion that is submerged in the oil. Now we know that the buoyant force is the weight of fluid displaced. Now the oil displaced by this is the volume of this fluid. Now the volume of this will be 10 into 10 into 6. This is the volume of fluid displaced by this. This is the volume into its density is given as 0.6. And then we have G. This is the weight of the fluid displaced that gives you the buoyant force. Similarly, the buoyant force of the portion submerged in water, this will be 10 into 10, which are the length and breadth. This will be 10 and then you have a surface that is going inside, that is 10, and this height is 4. So 10 into 10 into 4 times 1 into G. So these are the net forces that are acting in the upward direction. So if we add these two, what we get is, this is 600 into 0.6 plus this is 400 G. This is the net buoyant force. Now we know that since this object is given to be floating, that means this is a net buoyant force acting upward, it must be balanced by its weight downward. So this must be equal to m into G. M is the mass of the block, this whole block. So you can see G cancels out. The mass that we have is this 600 into 0.6 360 plus 400, we get is 760 gram. So if we look at the options, C is the correct option. 760 gram. We had to balance the forces and this gives us the answer. Let's do another question. Now if you see the question, this is a cubical block of wood 10 centimeter. This wood that is given in the question, it is of 10 centimeter on a side, floats at the interface between oil and water. Again, this is also floating at this interface like this. You see it's in between, it's transcending this oil and water interface, as in this figure 3. Now with its lower face 2 centimeter below the interface, it's given here that this is 2 centimeter. Below the interface, then the density of the oil is 0.6. This is again 0.6 given to you. The mass of the block is, what is the mass of the block? Now, as you can see from here, this lengths are given, this is given, this length is given, these lengths are given. Now again, it's given that since this is floating, that means the net forces are 0. This is 2 centimeter, that means this height is 8 centimeter. So what will be the buoyant force? The buoyant force due to the portion submerged in oil is, if we find out this is of 10 centimeter, this is a cube. That means its area is, this is 10, and then if you consider like a cube going like this is 10, this is 10. So you have 10 into 10, and then this height, this is 8 into 0.6 G. Similarly, the buoyant force due to water, this will be 10 into 10 into 2 into water. So it's 1 into G. Density of the water is 1 gram per centimeter cube. Now that means the net buoyant force, since both are acting upward, they will add up. It will give you 800 into 0.6. Then you have plus 200 times G. Now this whole thing must be equal to mg. Now one thing is important here is that it doesn't matter that what is the height of the oil or whatever is the height of this water in which it is there. What's important that if it's totally submerged, the buoyancy force doesn't change just because this oil will become of height 20 centimeter. Even if this oil is like this 20 centimeter, even then the equations will be same. There will be no change within it for the condition of floating. It will still be the same if the oil even is 20 centimeter of height. Even this is oil, nothing will change. The reason is definitely the pressure will increase at this point because it has more number of oil molecules, or you can say it has more weight of the oil that is exerting it on it. But at the same time what happens that this is also transmitted across this point. The increase of pressure that is happening due to this oil is also increasing the pressure at this point, and eventually both of them cancels out. So you can see there is no change just because these dimensions are given. So you have mg. If you find out the value, what you have here is 480 plus 200 G equal to mg. So it's 680 gram. G cancels out. If you look at the answer, it is this one is the correct answer.
So students, we have seen the topic of the buoyancy and the flotation. In the next topic, we are going to deal with the fluid mechanics, where we will be dealing with the fluids in motion. So stay tuned with Ask IITians for the next topic.